In this video, I'm going to show how test-driven development can be used to implement an algorithm. In this case, we're going to use the code kata bowling as the example code. The purpose of the bowling game kata is to write an algorithm that allows us to calculate the score for any bowling game. So the way that test-driven development work is that we need to start with having a test that fails. When we have such a test, we can write some production code to make it pass. When everything is passing, we can refactor the code, and when everything is still green, we can write a new failing test before we write some new production code. So that's kind of the iteration that we go through. So each iteration will be very fast, like half a minute long at maximum. So we will go through this this loop quite a lot of times. So on the screen you'll see on the left side, you'll see the production code that we're going to implement, and on the right side I have the test code. So right now you see that we actually don't have any production code, and we don't have a test either. So I'll start by writing a test. So the first test we're going to write is that we want to make sure that if we have a complete game of bowling where all the balls goes in the gutter, which means every throw is a 0, we get a 0 score for the complete game. First I'm going to instantiate the game. And right now we have a failing test because we don't have a class called game. So now I'm going to switch to my production code and create such a class. And we need to import to make sure that we have access to it. Then we're going to refactor. There isn't anything to refactor yet. So I'm going to continue writing test code until I get to a new failure. So we want to have 20 throws, because that's how many throws there is in a game of bowling. And we want to roll a 0. Again, the method roll doesn't exist, so now my test is failing. So I start by creating . Now my test is green again. And the final thing we need to do is to do an assert that we are actually going to get a 0 score. And again, my test is failing because score doesn't exist, so we'll create that. We will have it return -1. So when I now actually run the tests, we should see that it fails. So this is the test case. We assert that we expect to see 0 because that's what we told it, but we actually get -1 because that's what our production code tells us. So the least amount of code I can change to actually make this test pass is to add a 0. So now all my tests are passing. I don't really have anything to refactor yet. So again, I'll continue now writing a new test to test even more functionality. So if I have a complete game where I on every throw hit 1 pin, then I should expect to see a score of 20 because we have 20 throws. So again, I'm going to instantiate the game. I'm going to roll a 1. And we're going to expect to see a score of 20. I'm going to run the tests again. And of course we see that it doesn't work because we expect to see 20, but actually we receive a 0 because that's what our function returns. So now we need to introduce some extra code to actually keep track of the score. And now we can run the tests again to see that now we have green. Now we actually have something to refactor. One of the things to be aware of when doing refactoring is that if we have duplication of code, that's something we want to remove. So in this case we see that we instantiate the game in both tests. We don't want that, so we'll move that into the constructor to make sure that it's common. And then we'll just rename the variables. And we'll run the test suites again to make sure that we didn't do any errors. Again, we see some duplication. We see that we have this for loop more or less equal in both the tests. So we'll do some refactoring to make sure that that is extracted into a common method as well. Now I introduce variables to allow me to use the extract method feature for the IDE. I do this to make sure that I can do this mechanically and avoid me doing any typos. And afterwards I can actually inline the variables. And then I can do exactly the same up here. And remove the loop. And again we can run the tests to see if everything is still alright. It seems like it is. So now I can continue writing yet another test. So in case I have a game where I throw a spare, then I want to make sure that the algorithm adds the score for the spare. So I'll start by rolling a 5, and then I'll roll one more 5. This is actually the spare. A spare is dependent on the next throw to figure out what the bonus should be. So in this case we're going to roll a 3. And now we have exhausted 3 throws, but we have 20 in total, so we will roll 17 0 throws as well. So now we will expect to see that the first frame, which is 5 plus 5, which gives us a 10. The bonus is 3, that gives us a 13. And then we have a 3 as the second frame. So it should give us 16 as the expected score. And if we run the test, we'll see that it fails as expected, because we haven't added any code to actually take care of the spare. So when we look at this method, I would be tempted to add some code in the roll method to actually take care of the spare and figure out how to add that. But that would be a bad design, because the communication of the roll method is that it's concerned about the roll, but what it actually does is that it calculates a score where the score function, where we would expect to see the actual code to calculate the score, doesn't calculate anything, it just returns some pre-calculated score. So we have a design flaw here. So I'm going to comment out this test, because we are going to go one step back and focus on the refactoring. So now we have everything passing. So now I can do some refactoring. So I'm going to introduce a list of ints, which is our roles. Then we're going to run the test suite to see that we didn't make any errors. It seems that we didn't, and so now we can remove this unused score variable. So now we improved the design to make sure that we actually have the algorithm to calculate the score in the correct place. That should improve comprehension quite a lot. So now we're going to add the test again. See that, of course, it still fails. Now I would be tempted to do something like this. Because we have, like we see over here, we have two consecutive rows. They will give 10. And that should be a spare. But it has to be two rows in the same frame. It cannot just be two consecutive rows, because if they are separated across frames, then it's not a spare. So again, we have a design flaw. So again, I'm going to remove this test, and we're again going to go one step back to make sure that we fix our design issue. So instead of looping on the rows, I want to loop on the frames. So what I'm going to do is I'm going to first rename this variable to call it frame. And then we're going to say that we want to loop 10 times because we have 10 frames. And we want to do like this. So now we loop the frames. We have two rows in each frame. So we're going to add both the scores for each row, and then we're going to move forward by 2 to make sure that we go to the next frame. So if we run this test, we should have success again, which we do. And now I think we're ready to tackle the spare issue. So of course it's obviously still failing. So now we can do this. So now we know this is a spare. This is our spare. And when it's not our spare, we want to calculate just as we usually do. So a spare gives us a score of 10 for the spare, and then it adds the bonus, which is the next roll, which is I plus 2. And then again we need to increase the I so that we go to the next frame. So if you run this, now we have a passing test. So back to refactoring. So we have a few things going on here. We have, for example, an ugly comment saying this is a spare. We don't want that. If we can in any way make the code communicate this information directly, then it's much better than a comment. So in this case, I'm just going to extract this method and call it roll spare to communicate that this is we're rolling a spare here. We have the same issue over here. We have this. That's not really obvious what it does. We also have a comment, and so we have the same problem that the comment is. So we don't want such a comment. So again, we're going to extract the method, call it isSpare, because it's communicating a lot better. And then we can remove the comment because that's obvious from the context now. It also is non-obvious what I actually is. And we know that it's related to where we are in the actual array based on which frame we are looking at. So I rename this variable to call it frame index, because that's telling a much better story about what we're actually doing. I also don't really like the fact that we have add this part, but doesn't really communicate what it is, that it is the spare bonus. So I'm going to extract that as well and call it spare bonus, because again that communicates a lot better what we're actually doing here. So now we should have the tests running again and all is green. So now I can create one more test. So in this test we're going to test that we also handle strikes and the bonus of them. So we're going to roll a 10, which is a strike. Then we're going to roll a 3 and we're going to roll a 4. Because the strike bonus is dependent on the 2 next rolls. There are 10 frames in bowling, and we used, this is the first frame. Then we have, this is the second frame, then we have 8 frames left. There are 2 throws in each frame, which means we have 16 rolls left, where we are going to hit 0. Then we're going to assert that what the score is, and we're going to get a 10 for the strike. Then we're going to get the bonus, which is 3 plus 4, which is 7. So this frame is going to give us 17, and then we're going to have 7 for the next frame. So that's going to be 24. So when we run this, we would expect to see that it fails. So now we can add again code to handle this case. So if we actually have a strike, then we want the score to be 10 for the strike itself. We want it to be the 2 consecutive rolls. And since the strike only uses up one roll, we just increase the frame index by 1. So let's see if this gives us a green test. It does. So again, we have exactly the same problems as before. We have an ugly comment that we don't want. We will much rather extract this method and call it roll strike, because it's again communicating a lot better. We have the same thing up here, and you can probably already guess that I'm going to extract that and call it this strike. Remove the comment. Then we have the bonus calculation. And for some reason my IDE doesn't want me to extract that directly, so I have to move it a bit around. and then inline it. And again, we can test that everything is still working as we expect it to be, and it does. So the final test I'm going to create is to make sure that we can handle the perfect game. So I'm going to roll all strikes in the game. So 1 strike per frame, that's 10 strikes. But to evaluate what the final strike gives of a bonus, we need 2 more rolls. So in total we have 12 rolls with 10 pin-ins in each. And it should give us a score of 300. So let's see if that works as expected. It does. So this is the bowling game kata. I hope it showcased how TDD can actually help you drive your code into a good state. This is by no means a complete system. We still have the potential to add stuff like input validation to make sure that we can't do invalid stuff. We could also add some additional requirements that it would be able to calculate a running score and other aspects of the bowling game. Yeah, but I hope this gives you some insights into what TDD is and how it can help you make better code.